Answer.
Hello, Muslim. Good evening.
Sir, can you hear me, sir?
I'm able to hear. Tell me.
Okay, okay. Yes, so that's what. That's a little bit stuck because of setting and all here.
Okay, no issue. We'll wait for 1 or 2 minutes or what?
2 minutes, sir. 4:58 is there, so another 2 minutes, sir.
Okay, definitely.
Hello, sir.
Yes, please.
Sir, we can start, sir. Sir.
Okay. Just 1 minute.
Sir, hello.
Yeah. Tell me.
Sir, coming Wednesday, na sir. Most of the people will travel.
Diwali, I know.
Yeah.
Okay, no problem. We'll compensate some other day.
Okay, sir. Right.
Leave granted. I know Diwali is important because
Thank you, sir.
first time you are getting on Thursday, correct?
Mm.
Tamil Nadu government
Right.
also given on Wednesday, Friday leave so that you
Yes.
can enjoy the entire week, 4 days. So
Right, sir.
no problem. No problem. We'll compensate some other day. Like this.
Right, sir. Right.
Absolute no issue. Getting long leave is very rare, right? So I want to, that's not issue. Okay, 1 minute. I will switch off lights to get a glaring. I'll come back. Just 1 minute. Screen is visible?
Visible, sir. Visible, sir.
Okay. Okay. Good.
Sir, I'm sorry for interrupting right
Yeah.
before
Yes,
the
please.
match. Sir, there was an image of optoelectric sensor, no, sir?
Yeah.
Can you just
Yeah.
go there? Sir, I was of the opinion that for wheel speed sensors, we use optoelectric sensors because that's what my peers had told me or mentors had told me in company. But we also discussed about the other kind of sensors in the class, right? Like capacitive rotational sensors or something. So
Inductive.
between
I
them,
told inductive.
yeah, inductive. So like amongst
That's
them,
what
which
you are
is
seeing
better,
on the
sir?
screen now.
Yes. Among them, which is better, sir?
See,
Optoelectric or inductive?
optoelectric is better, but only thing is dust problem. That today you listen to it, then you'll understand.
Okay.
Nice that you will understand. Okay. So yesterday we were talking about importance characteristics of sensors, correct? Yeah. We talked about stopped here. Okay. Am I correct?
Sir, correct, sir. Correct, sir.
This slide.
Yes,
Okay.
yes, sir.
So input output as a linear is better, but most of the sensors are having different type, binary type, for example, which can detect whether input value is more than certain value or less. EGO sensor, binary type, which when exact oxygen, correct? Then exponential type, logarithmic character, all this thing. What is advantage? These points already you noted, I think. So today we'll go to Another it's important some more parameter, what you call it as graphics and another sensor parameter. Already we talked about sensor, correct? We started with input range, output range, sensitivity. We have talked about sensitivity, then resolution. The 1 minute. This is giving some small issue. Just a minute. Still visible, correct? Screen is visible. For you.
Yes, sir.
So resolution,
Visible, sir.
yeah, precision and history, all these things. This I am showing in a graphical form to understand better. So if sensor is linear, input-output characteristics. So you can see that this is the x-axis input vary from 0 to something, some value. Maybe pressure, temperature, whatever, maybe force, whatever the input parameter. The sensor produces an output. Generally in the order of millivolts, I told you, most of the sensor produce a voltage. Few sensor produce a charge. Correct? Piezoelectric sensor, we are going to see that. Few sensor produce current also in the order of milliamps, 0 to 10 milliamps, 0 to 20 milliamps, something like that. That's how they work. But many of sensors, they produce electrical voltage in terms of 0 to 100 millivolts, 0 to 50 millivolts, or 0 to 1000 microvolts. Very few, correct? So that's what. If the input-output relationship, the input is varying from 0 to some maximum value, output also start from 0 to the output maximum value. And as I input change the input, the output is coming, appropriate output is coming. Now I connect those things, then I get a straight line. So if it is a straight line and having a slope, what you call a linear sensor, that is best, correct? But sometimes I told you there can be a offset. We talked about a sensor with offset. Normally it is supposed to be like this. This is what this one, this red line. Normal sensor when it is a sensor is new. But if you have overloaded your sensor or become aging, even when input is 0, you can see that there is some output. Right? The sensor, for example, force sensor is there. 0 to 100 Newton force. Right? That is the sensor range. It will produce 0 to 100 millivolts, for example. Okay, this is what was new sensor. You are using for a long time. Sometimes you have overloaded maybe 150 Newton also, sometimes by mistake or something. What will happen? The sensor is a little bit deformed. If it deforms, what will happen is even when there's no force, sensor will produce some output. Correct? Instead of 0 millivolt, that is called as sensor offset. That is not desirable, but still you can use the sensor as long as the sensor offset remain constant. Now what I am giving 0, it is giving, say, for example, 10 millivolts. I give 1 Newton force, it gives, for example, say 11 millivolts, something like that. I give 2, accordingly it increases, correct? 12 millivolts. That means there's a permanent 10 millivolts offset is there. That is not desirable, but that still you can use this sensor. That's what you said. Then next one, important sensor, already we talked about output range, input range, output range. Input range is 0 to, for example, I say 100 Newton is the input. So it will produce 0 to 100 millivolts. So this is called as output range. This is called input. Maximum value minus minimum. What is maximum? 100 Newton minus 0 is called as 100. This is the range, sensor input range, That's what is shown here. The x-axis represents this one. Similarly, output range is nothing but 100 millivolts minus 0. When the 0 input is 0 millivolts, when the sensor was new, correct? That time it got 100 is the input range. That is maximum value minimum. Then we already saw what is definition. Then another thing also people call what a dynamic range. Correct? Dynamic range is when input is varied from 0 to maximum, output vary from 0 to maximum. This is called as dynamic range. Sensor dynamic range is nothing input versus output. Dynamic range of sensor. When I vary my input 0 to 100 Newton force, it produces 0 to 100 millivolts. So this is called as, just 1 minute.
610 இன்னும் ஆட் ஆகும் பண்ண முடியுமா கேட்டதுல
Sorry, some visitor came, they were waiting outside.
Sir, no, sure, no, sure. Please, please.
Okay, so this is what this one. The next one is what we call as the sensor should be linear. Sorry, just wait 2 minutes.
Might come me.
Sorry, some BTech students, they want my advice. I don't know how they are coming now. That's why 1 or 2 times they are standing outside. One by one they are coming. I told them to come group by 4:30. They did not appear 4:30. Now they are coming one by one after 5. What to do? That is the
Okay, sir, no
student.
issues, sir.
Sorry, this is what the students sometimes, I told come between 4 to 5 as a group. And now they are coming one after another. Okay, fine. When we talk about sensor, we want a linear this one, but here you can see that the sensor is a non-linear response, correct? So the blue color is non-linear. Originally expected is the red color, that is best. But some sensor will have like this. No, you can't help it. Sometimes some sensor may have like this. It may go like this and come like this. When increase input from 0 to, say for example 100 Newton, same sensor input, the output is 0 to 100 millivolts. No, but instead of going this straight line, it may go like this. You can see that I am drawing it can go like this and reaches value for 100 Newton. For example, this is 100 Newton. It has come with 100 millivolts. But if you reduce by 199 later, when you reduce, it is supposed to follow this path. No, it won't follow. Instead of that, sometimes it may take a different path. From here, it is reducing. This also non-linear and still bad. Up and down is taking different path. There are sensors like that, you can't help it. Okay, that one thing. So this kind of behavior is non-linear. Then, sometimes some sensor may have this, again, another sensor with hysteresis. Correct? While increasing input, 0 to, for the same 100 Newton force, the output 0 to 100 millivolts, but it was taking blue color path. That also not straight line. You can see that it is non-linear. Non-linear means it has different slope. Here one slope, here one slope, and here different slope. The slope of the curve is varying. Then it we call non-linear. For given delta x input, delta y is not equal. Here it will be equal. Like if I take delta x is this much, delta will be here. Wherever I take same amount of input delta x, same amount output will come. That is linear sense advantage. Non-linear means here you will have more. When you come here, this place, you can see that for same delta x, the output will be very, very small. So that is why we call non-linear sense as gain equal to different. Input output gain is different. Output divided by input for delta y divided by delta x is got gain. That what we call this one. That is not going to be same. So then this sensor you can see that when I increase 0 to 100, it goes in the blue color line, it reaches maximum, and a reverse it comes. It takes two different, but this is called a hysteresis. Few sensors, magnetic measuring sensors, some sensors have this kind of hysteresis. That's not good, but you can't avoid. Some parameter when you measure, those kind of sensors will have this kind of hysteresis. Okay. Then when we talk about sensor, we saw many sensors, correct? So when you talk about sensors, sensors also can be classified based on three important this one type of the sensor, as I told, resistive type, inductive type, or capacitive type, or it can be photoelectric. We are going to see later, or piezoelectric or thermoelectric subsequent classes. But today what we are going to say is input output capacitor. We say mathematical model, correct? You can take the data. As I told you, my input is varying from 0 to, say, for example, 100. My output is also varying from 0 to, say, 100%, whatever it may be. So if you apply 0 means output is 0. When I apply set 10, it produces some value. If I apply 20, it produces something like this. That means now you connect this, correct? Connect this, you get a curve. This curve you can write as a mathematical equation. That is what the sensor model. If the curve fit, correct? First you vary the input from 0 to maximum. You get output 0 to maximum. You plot the curve, correct? You may get a straight line. You may go. Okay. Hello. Yes, please. Abhijit. Any doubts?
Sir, I think he got accidentally unmuted.
Oh, okay. Okay. Yeah, I thought he's asking some question. Okay. So when
Maybe
you
can mute him from your side, sir, I guess.
Okay. So this is what best. When I change it, then if I fit a curve, you can get curve like this. You get a straight line curve. Then you know that y equal to mx plus c. Correct? Mx plus c. This is offset. Here the offset is 0. M is called the slope. Correct? X is called input. Output equal to, that is straight line curve. This is equation of straight line. So if the curve has, that means I can, this is the mathematical model of particular sensor. I can say that mathematical model of particular sensor whose input output in a straight line. So then the M, all this thing, if you know that, you can write your mathematical model. Correct? This is called a mathematical model of the sensor. Similarly, you have data. Correct? This curve is like this. You can curve it, then you will get an equation. Again, there will be equation. It will be a spline equation. Correct? That equation is called the mathematical model of the sensor. Okay. Now, using mathematical, what you can do, if I vary my input, and if you know the M, slope M is already known, C is the offset is known, and if I vary the input, Y can be calculated. That means even without having sensor, I can find out what my output. That is advantage of mechatronics. Correct? Already you know the modeling a system, sensor, actuator, and applying various input as a program. This is called as virtual modeling of sensor. Further, what do you need? This mathematical equation of the sensor. Correct? It can be a straight line equation, it can be a spline equation, or a semicircle equation, or different this one. So that is called mathematical model. And the sensor model can be algebraic equation, simple algebraic equation. So I said y equal to mx plus c. Correct? If I say this is the equation of your sensor where it has only addition, subtraction, multiplication, division. The equation consists of then that equation is called as algebraic equation. If sometimes you may get an equation something like a dy by dt, sorry, dy by dt equal to dx by dt plus kxt, something is there, correct? X is the input, y is the output, and k is the constant, and x of t is the input, correct? So what is this equation? This is a first order equation, first order differential equation. Sometimes you may have d square xt divided by dt square plus dx by dt plus kx plus t equal to 0. You may get an equation. So this equation is called second order differential equation. So if you model your sensor, you may get a simple algebraic equation, or it can be first order, second order, third order, like that. The equation can be like that. Already we saw modeling RLC circuit, correct? We had a spring mass damper system. We saw hydraulic actuators. Modeling already saw. So same way, sensor also will get a differential equation or algebraic equation. If the equation what you are getting, y equal to mx plus c, correct? This is algebraic equation. If the equation like this, it has only algebraic terms, multiplication, addition, subtraction. That sensor is called zeroth order sensor, correct? You apply input. What you did? You applied input 0 to v in, that is maximum, input maximum, and you noted what is the output 0 to maximum. You connected the point data points, correct? This is called calibration. This calibration curve is a mx plus c, y equal to the straight line. Then that sensor is considered zeroth order sensor. This is mathematical order sensor. It is algebraic equation. Then sensor is called zeroth order sensor. Okay. Then instead of that, same thing you did, you are getting a differential equation. Dx of by dt plus kx plus t equal to f of t input. Input is this one, correct? Sorry, output. This is output of sensor y of t, and then x of t is the input. Well, then if the equation is first order differential, that sensor is called first order sensor. Similarly, if you get a second order d square xt divided by dt square plus dx by dt plus kx plus something is 0, then it is called as a second order sensor. Please notice sensor, not a sensor itself have many components. We are going to see that, for example. So the sensor can be third order sensor, fourth order sensor. Most of sensor fall within this category. 0th order, first order, second order. Most of sensor what we are seeing, correct? If we talk about strain gauge, what type of sensor it is? Anybody?
Sir, it's a first
Resistance.
order distance.
Is a first order sensor strain gauge?
0th order?
Yeah. Why?
Because it is like a spring.
Yeah. Input output relation is only algebraic equation. Right?
Yes, transfer function relation.
Transfer function is a simple algebraic equation, so it is called zeroth order sensor. Okay. So the first order sensor will have first order different this one. Now we'll see the example. Zeroth order sensor example, for example, potentiometer. TPS sensor. TPS sensor is nothing but a potentiometer. It has 3 terminals. You can see that 1 terminal, 2 terminal, 3 terminal. So the last 2 terminals are called fixed terminals. Correct? Definitely you would have seen the potentiometer in your lab or radio, TV, you would have bought. So it will look like this. So this is a shaft. If I rotate this shaft, correct? This is body. Inside that you have a circuit, what you call as a track, something like this. You have a non-conducting backlight on which they put the ground carbon particles. Ground carbon particles, they make as a paste. The paste will be coated on the semicircular face like this. Okay, and one end is this. I say terminal 1. The other one is terminal 2. This last one, 1 and 2. The center one I call 3. And what I do is I have one moving contact touching this carbon paste. Okay, now this is 1, this is 2, this is 3 moving contact. Between the end, what I do is I connect a voltage, for example, 10 volts. Okay, here I am applying 10 volts. So between the last 2 ends, 10 volts is there. Now we know that this is we call a ground. I will take a multimeter, correct? Our voltmeter connected to like this voltmeter, and other end is connected to moving contact. Okay, when the moving contact is here, it will show 0 volts. Okay, the voltage is the 10 volts is dropped from here to here linearly. Here will be 10 volts. If I measure here, it will be 8 volts. If I measure, because this is the resistor represent, that is nothing but this carbon track. So if the moving I given the negative here plus, when moving contact is like this, let me use different color, you will understand. So with the moving contact touching here, this is the ground. So there's no voltage up. If I measure the voltage up in moving contact, this is on 0 volts. Okay. Now if I move contact like this, it has come to, no, it may be 1 volt. If it comes here, it will be 2 volts. If it is here, 3 volts. When it is middle position, it will be 5 volts. It will be 5 volts. Now, if the moving contact touching here, that means I am rotating shaft. If I rotate my shaft, the moving contact is moving like this. If it comes here, 10 volts will be there. That's what. So this sensor is a zeroth order sensor. Output equation equal to y of t equal to k into xt, where xt is the position of the shaft. Xt is nothing but theta. Theta of the shaft. Theta of the shaft varies from, for example, 0 to 180 degree, for example. It can, correct? Most of potentiometer where 0 to 270 maximum, not more than that. You cannot rotate to 360 degree. Potentiometer, there will be a stopper inside. It may vary from 0 to 270 degree or 0 to 180 degree only you can rotate. Now, I given, how much I given? 10 volts to this. 10 volts I am supplied and this is my output with respect to negative terminal. In that case, what do we get is, if the 0 degree, for example, take that is 0, rotating 0 to 180 degree, 0 to 180 degrees represented by 0 to 10 volts. That is output. Moving contact. Moving contact is moving from up and down. When the moving contact here, 0 volts. When moving contact middle, it will be 5 volts. When moving contact comes here, it will be 10 volts. So that means we know that if I move 1 degree, theta is moved by theta of t equal to 1 degree, 0 to 1 degree. The delta theta is nothing but 1 degree. What output voltage? 10 divided by 180. Correct? Is the output you receive for 1 degree movement of shaft. How much it is? We can calculate. Not 5 volts, not so that is nothing but I will get 0.055 volt or 55 millivolts. If the shaft is rotated by 1 degree, the output will be 55 millivolts. If I rotate by 2 to 1 degree, 2 degree means it will become 110 millivolts. So you can see that if I rotate 180 degree, it will be 10 volts. So if you draw the plot, it will be like this. Straight line, cow fit is straight line. So this sensor is a zeroth order sensor. Okay. What is the advantage of zeroth order sensor? That is best sensor. Input output is easy straight line. And suppose I know that my input is varying from 0 to 180 degree and my output is varying to 0 to 10 volts. If the shaft is middle position, being a straight line, always I can say that 90 degree means it will be 5. Correct? So maximum value, minimum value, from that always you can find the slope. From slope always you can tell. Very simple, straight line. And the only potentiometer is 0. So advantage, it is linear input output characteristic. And zeroth order sensor doesn't have storage element like capacitor. It is made of purely resistive element. Zeroth order, because potentiometer resistor, right? It has the only resistive element. It doesn't have capacitive or inductive. No capacitor, that is called storage elements. So because of no storage element, hysteresis will not be there. It will not be non-linear sensor. Like a first order sensor will be like this. The output characteristics, or it can go like this. This will be a straight line, that is better. And infinite bandwidth. It has infinite bandwidth, these sensors. Example is the potentiometer. Very few sensors are zeroth order sensor. Okay. Next one is called what you call first order sensor. If you have first order sensor, the input output character represented by a first order differential equation. Okay. So this is in a time domain equation. Right? A0 and A1 is called coefficient differential equation. Already you know that. That depends upon what? Any idea? Already we talked. A1, A2 is coefficient. This one depends upon what?
Depends upon what kind of system that is, whether it's a mass kind of a system or a resistance or something like that.
Yeah, you are correct. Almost 99 close. It is
But
called
it will
system
come,
it is
it
called
will
as system
convert into time
parameters.
constant.
System
Yes.
parameters.
Yes.
Correct? System parameter. Time constant is output. Correct? The coefficient
Yes.
also all depends on system parameter. Spring mass number, mass, stiffness, and damping constant. Correct? So, like that, any system, that is called system parameter. Mass or resistance value, inductance value, capacitance value, electrical system. They are going to decide what is the coefficient A1, A0, all these things depends upon system parameters. Mathematical model itself represent in terms of system parameters. And time constant also depends upon system parameter. Output Y of t also depends upon, Y of t is also output also depends on system parameter. Why? This is going to affect, coefficient going to affect, coefficient nothing but, for example, what is damping ratio for spring mass damper system? We already talked mathematical, you wrote exam also. Delta or eta. What is the equation for spring mass damper? Anybody?
The KD by
C-
CC, sir. KD by
C,
CC.
CC divided by something?
KD by CC.
Ah, very good, very good. Correct. So where KD or C or D, sorry, B, these are they called damping constant, damper divided by CC. CC equal to what? Root of 4 mk. M is the mass, K is the stiffness of the springs. CC equal to root of 4 mk, and K is damping constant. This is a delta or eta. Correct? So these are called system parameter. M is system parameter, K is system parameter, and KD is system parameter. Damping constant, spring stiffness, correct? K, and M is the mass element. Then CC is a critical damping constant. That is one of the output. Delta eta also is called as output of system, damping ratio. And also time constant T. T equal to root of K by M or M by K. We will see. Maybe you can recall. We'll see later. Don't worry. Okay, fine. If the equation is a first order differential equation, then system is a first order sensor. Then this is a time domain equation. Already told you generally doing calculation, all those things, immediately convert Laplace. If I convert the Laplace and train the transfer function, what is transfer function? Output divided by input. Output is called Y of S, input is X of S. The transfer function will be like this: 1 divided by A1 into S plus A0. A1 is the system coefficient, is called as coefficients of differential equation, which depends on system parameter. That's what we are going to do. Here it will be represented K divided by tau into S plus 1. Correct? Where tau is called as time constant of the system. K is called as a DC gain. The K is called as DC gain. So I can write the equation Y of t, output Y of t equal to X of t into 1 minus. Correct? This is final, this one. The output of the system Y of t equal to X of t, input multiplied by 1 minus e power t divided by tau, where tau is called time constant of system. We are going to see time constant dependent upon system parameters. Now, example for first order system is, for example, take a temperature sensor, right? Thermometer, mercury thermometer. This is a mercury thermometer. Mercury thermometer is an example for first order system. Here we are showing that a vessel is there. In vessel, it is filled with some fluid. It is filled with some fluid. For example, temperature 50 degree. Okay. Now I took my thermometer. When thermometer was like this bulb, what is the temperature of the thermometer? What will show? Room temperature. Correct. For example, in my room temperature now is, let's say, 25 degree centigrade. So it was this one. Suddenly, I dipped this one at t equal to 0 time. Correct. I dipped my thermometer inside the water like this. The temperature sensor is the water is 50 degree. That means there's a step input I have given. Okay. Now, what is variation? 50 minus 30 is, 20. I said 20, no, 25. That means 25 degrees is the delta T. Temperature sudden changes 25 degree. That is, I represent as a normalized value. 25 degree. This is the red color. That is my step input. It was 25 degree. I suddenly dipped my thermometer inside, went to 50 degree. This normalized value 25 I made as a 1. That is called unit step function. That is represented in red color line. Okay. Now, the green color is now you know that it was the 0. The temperature will be start increasing. The indication, correct? I will show some other color, maybe green, maybe. So what happened? The mercury inside, from here, the heat will go. Heat from this one will be go inside my thermometer bulb. Inside which I have the mercury. Mercury is get heated up. Mercury column rises like this. It slowly rises. So it comes to 50 degree. Initially it was showing 25 degree. Now it has increased to 50 degree. Okay. So to do immediately will not. I dipped inside at T equal to 0 seconds. So the input sudden change happened because it was outside 25 degree. I dipped suddenly in 0 time quickly so that the thermometer bulb is exposed to 50 degree. That's what is a step input. The difference was 25 degree delta T. Now, from then the mercury gets heat from the Q, from the water, and the temperature through glass bulb. See, it is made of the thermometer made of glass bulb. The glass bulb has some thickness material, so the heat has to go inside, then heats the mercury. Mercury volume increases, the mercury column rises. That's what. So the rise in mercury column is represent green light. That's what indication. So it takes some amount of time to measure and tell you what the temperature is. Okay. So here it is 25 degree. It has to go to 50 degree. This is 50 degree. Let me clear this. So this is 25 degree. This is 50 degree. Okay. Now from here it is increasing. To reach, see the shape of the curve, it is called exponential curve. First order system output, if I give a step input, the output will be exponentially increasing. But if it is zeroth order system, how it will be? Anybody?
Straight line.
So it will be linear.
Straight line.
No, it will be like this, exactly over that, immediately. Correct? So input change, output also changes, exactly overlaps. You can see the violet color. Zeroth order sensor, if I give a step input, output also step. That is the best.
Sir, if it increments over time, then it will also be like a step response, right? Like a set of steps.
See, that called ramp input. If temperature is varying like this, if temperature is rising like this is called ramp input. If temperature is varying like this, where this temperature, you are heating, correct? For example, you have a burner and you are heating the water. Initially 25 degree, already thermocouple or dip. At that time, you are 25 degree water temperature, room temperature showing. Now you are heating Q, heat. Then water temperature increases 26. That means it is increasing linearly, right? Then output of the thermometer also will increase like this linearly. How it will be? If it is a first order, this one, it will be like this. It will be like this. This is a sensor, that is thermometer indication. It will not immediately show 50 degree. You are increasing heat, water heat also increasing, thermometer also measuring what is the rise in temperature. That is called ramp input. If I suddenly dip, that is called step input. For step input, you will have exponential like this. Okay. Now, this system, the mathematical model of thermometer is this, no doubt. U into A multiplied by within bracket T actual, that means water temperature. Water temperature 50 degree and T indicator is the indicator temperature by thermometer. There is indicator into dt equal to M into C into DT indicator. This is called DT indicator. That means variation in indicator temperature. So this equation, this is the mathematical model of the mercury thermometer. Okay, in which what are system parameter? One is called U. U is called heat transfer coefficient of the glass, because this is made of glass, no? Mercury thermometer is made of glass. Inside it you have filled with this one. The bulb is there. Bulb is made of glass. His heat transfer cancelled. What type of glass material? Right? It has a heat transfer. This one. A is the heat transfer area. The thermometer bulb. For here I am showing generally thermometer will be something like this. Correct? Generally mercury thermometer will see here like this, something like this. Here will be mercury. But for understanding purpose, we made this like a bulb like this. This is filled with mercury. Correct? Spherical. So in that case, the surface area of this sphere is the heat transfer area, through which only heat is going inside the mercury. Mercury receiving heat from water or wherever, whatever temperature you want to measure. Then T actual is the indicated temperature by thermometer. Actually is water temperature indicated. M is called as a mass of the sensing element. What is mass here? Mercury mass. Maybe few grams, 1 gram, 2 gram, 3 gram will be the mercury inside the thermometer. That mass. C is the specific heat of the sensing element. Again, the mercury. Correct. Once you know that, then you can find out. So I can write a transfer function of this system is nothing but T indicated by T actual. Input divided by, output divided by input is called transfer function. G of S is nothing 1 divided by S into tau plus 1, where tau equal to this. This is called a time constant. Tau is called as time constant of the thermometer. Please note that again, time constant depends upon M, C, U, and A. All are sensor the thermometer parameters. M is the mass of the mercury. C is the specific heat of the mercury. Right? U is the heat transfer coefficient of the glass bulb, thermometer bulb. Then A is the area of this one. So finally, time constant depends upon this material. If I want to, what do you want? Time constant, what do you want theoretically? When we talked about modern mechanical, also we talked about how much you want. Value should be your wish. 100, 200, 1,000, infinity, 0. What do you want?
Minimum, sir, 0.
Your wish is 0. 0. Time constant is 0. Yes. For which sensor? This sensor has 0 time constant because there's no storage element. 0th order sensor, which has energy dissipating element, will have time constant equal to 0. Okay. First order sensor has a storage. That's why you are getting differential equation. Okay. Note down this equation. This is an example for first order sensor. Now we'll go to second order sensor. Example for second order sensor is, for example, accelerometer. That is nothing but accelerometer used for measuring acceleration. This is a typical accelerometer, correct? Which is called seismic mass type. Note down. Seismic mass type accelerometer. Okay. So you can see that this is a body which is maybe cylindrical in shape. Generally, it will be in cylindrical shape. Okay. We are showing what we say cut section view. From top, you'll see it will be a circle, correct? So inside that, you have one mass, which is called as mass. Please notice spring mass damper only. Similar to spring mass damper system only, but that can be used as a sensor. You have a small mass, which is called seismic mass, which is supported by a spring and a damper. The spring has spring constant Ks, damper has a damping constant C. I told you damping has some book put C, some book put B, some book put KD. Don't consider all are same. Because many books avoid KD because KD is used for proportional derivative control gain. PID control, all this control system they call KD is called a derivative controller gain. So that's why many books don't use KDs, but some books are using. KD is as a the damping constant of damper, but majority of book we use C or B convention. You can use anything. Nobody is going to question you. But this is convention. Repeat. I'm saying, don't come and say, sir, I saw some other book, some other letter was they're using. They can use anything, whatever they wish. Okay. So this is there. Now it is supported. It is a spring mass damper system. Correct. Already we know spring mass damper is a second order differential equation. Correct. A2 into d square by dt divided by dt square. A1 into dy by dt. A0 to y of t equal to x of t, where x of t is called input. Y of t is called the output, which is nothing but displacement. And this is called acceleration. This is, velocity. This is acceleration. Now, this is a time domain equation of the accelerometer, which is nothing but a spring mass damper system. Apart from that, you can see that it has a mass element, one spring element, and K this one, and it is housed inside a cylindrical metallic this one, and it has one displacement center. One displacement sensor also inside, which is going to measure the displacement of this mass. This mass can move up and down. Because please know that it is supported by a spring and a damper. And if I give a motion, correct? Suppose I take this accelerometer attached to a object, correct? You have object which is vibrating up and down. That means what I know, it is firmly fixed. Okay, that means if the object moves on up and down, the whole sensor also moving up and down. It is moving up and down. In that case, what will happen? The force coming from will be going to the damping and this one. We know that spring and damper is called shock absorber. The motion, the force, what is coming from the object will be transferred to the body of the accelerometer because the body is attached firmly, and which in turn will be transferred to the spring and damper. But these things will absorb some amount of energy. A small amount of energy depending upon this. We already saw, again we are going to see it. The shock absorber maybe absorb 80% or 60%, 70% or 90%. So remaining percent force will come here. Because of that, this seismic mass also will go up and down. The movement is called a X naught. The seismic mass movement going up and down here is called X naught. The vibrating object is moving up and down. This motion is called X in. I am vibrating, wantonly moving the object up and down, so that the sensor also is moving, body of sensor also moving, but the so shock absorber, this is nothing but spring and damper absorb some energy. All the force is not going small. Because of that, this element also moving up and down. Okay, so now we know that. Now that we can write a differential equation, correct? So this is a transfer function of the general second order system, which is represented by second order equation, A into this one. For this one, we can write the equation. So this is called a free body diagram. This is called a free body diagram. Free body diagram represents what are forces acting on the given object, the sensor. So now there's a force Fm, correct? Which is equal to M into X naught double dash. Okay, X naught double dash. This is nothing but displacement of the seismic mass. If I do twice I differentiate, I will get what you call as acceleration. This is acceleration, and then this is the mass, seismic mass weight. Mass into acceleration of this seismic mass is represented Fm. That is moving up, because suppose the force is acting upward from the body, some amount of because of this vertical. Then there are two forces acting downward. One is called spring force. The spring is this object wanted to move up due to the input force, but these two, spring force and damping force, is pulling down. This is called damping force Fc, and Fc spring force. They are pulling down. They are acting against the movement, vertical movement upward. So this is called a free body diagram. From this we can write the equation Fk. Spring force equal to K is Ks is spring stiffness multiplied by X minus X in. Sorry, X naught minus X in. X naught is the displacement of seismic mass minus X in is the sensor, correct? Body of the sensor which is attached to vibrating. This is the vibrating, that movement. Okay. Similarly, Fc equal to damping constant C multiplied by velocity difference. X naught dash is the velocity of seismic mass. X in dash is called as the velocity of vibrating object or sensor body. So that can be written as Fc equal to C into X, or this is R represents relative velocity between the seismic mass velocity and the body of the sensor, which is nothing but same as a moving object. So these two are known. Then we can write with the relative displacement or this one. I can write like this: relative displacement XR equal to X naught minus X in. X naught is the seismic position. X in is the body of the sensor or nothing but vibrating object position. It is also moving up. Both are same. Okay. Now, as per this one, we can write some of the external forces are the seismic mass. My interest is seismic mass position X naught. That can be a summation of Fx equal to M into X double dash. We can be written minus Fc into minus K, because we know that these two forces are working downwards. This is going upward. That's why we got a minus sign. Is the upward, this one Fm. So based on this only we have drawn the diagram. Now we can say that the acceleration of the seismic mass double dash X naught double dash equal to X r double dash related to this one plus X in double dash. Acceleration of this body is nothing but X in double dash is acceleration. This is the relative acceleration between these two is nothing but acceleration of the seismic mass. So that can be written like this. Correct? Please take the derivation, because you can expect this derivation may be asked in the exam. and some values will be given. You will be asked to calculate what is the acceleration, something like that. Take the derivation. Okay, so now I can write this as minus Ks into XR minus.
Sir,
Yes, please.
why is it negative of Fs minus Fs and minus Fks, sir? I didn't understand that fully.
No, they are acting
uh,
against, no. The net, see, the summation equal to 0.
Okay, they're opposing forces. Okay.
Summation should be 0. That is what the Newton's law says, no, motion. Forces acting against and to this one, if you sum up, it becomes 0. These forces,
Okay.
net force will be 0. Okay, so then I can write like this. From this, I can write the equation in terms of acceleration. The seismic mass multiplied by is acceleration. That is relative displacement. This is relative acceleration plus the damper constant multiplied by the relative velocity. Mass into relative acceleration plus damping constant multiplied by relative velocity plus Ks is the spring stiffness into relative motion equal to input acceleration. Correct? M into X in. X in is nothing but double dash is nothing, input acceleration. This is the mass. So this is the final equation. You can see that. That means I can use my spring mass damper system to measure the acceleration. Correct? So now if I take it next level, from this we can understand that the acceleration of the seismic mass is directly proportional to acceleration input. So that means if I measure the acceleration of the this one, which is nothing but the differentiate twice. If I know the displacement, correct? X naught I know. If I double time differentiate, correct? D by dt and again d by dt. Correct? That is going to be get X naught double dash. So I can measure the velocity using the sensor. Acceleration using the sensor. That's what. So the output is proportional to input acceleration. Okay. Now we can know that in second order this one, the behavior of this is a second order system. The equation is second order system, correct? The equation of this system is a second order because it has the spring and the mass element. Already we know that. Now this system has a natural frequency, correct? Omega n is nothing but root of Ks divided by f. This is what I was asking, right? For natural frequency we are asking, and damping ratio is C divided by root of mks. This is called Cc, critical damping. This is the damping constant, damper. This is a damping ratio. From above equation we can write like this: 1 by omega n. Omega n equal natural frequency of the sensor. Please note that it is a spring mass damper system, so it has a natural frequency that is given by this equation. Okay, stiffness of the spring divided by m. Please note all three are inside the sensor. A seismic mass, a damper, all these things enclosed together is called accelerometer. And there's a displacement sensor which measure the displacement. Actually measure the relative displacement between this and this. That's what the sensor. One sensor is there. This sensor output is coming from that, you can always find out. So I can write the equation 1 divided by omega n square plus xr is the relative displacement double dash acceleration plus 2 into epsilon divided by omega n into velocity xr dash, which is velocity of this one, plus displacement. Xr is the relative displacement. That means x naught x in minus x naught. That is called relative displacement equal to 1 divided by omega n square into this one. So this is input acceleration. Okay, so this is the relative acceleration of the seismic mass. Nothing but that is the sensor output. So that means both are related by this is related. If this is varying, this also will vary. How much it will vary? Depending on 1 by omega n square. So if I'm able to measure this this displacement, from that I can get xr double dash. So this is how the sensor measures. Okay. Now last one, just I want to see here. If a vibrating object subject to sinusoidal vectors, I told you the input this here you are giving a vibration. If the vibration itself is sinusoidal in nature, that means the vibration V that is x in. X in is a vibration 0 to x max positive and minus x max. I say that it is varying in sinusoidal shape. They represent x into sine omega t. This is called as the amplitude. Positive, negative, this is called, that's what we are calling. X in is nothing but amplitude, y-axis. Then omega is the frequency of this one cycle, omega t is this one. Then this is the input. Output of the seismic relative motion of the seismic mass also will be xrt is equal to xr into sine omega t plus phi, where phi is called phase shift. That's the relative phase speed. That means the seismic mass movement, relative motion also will be like this. Please note that it will be like this. This is called a phi, phase shift. With there is a, we know one cycle equal 360 degree. The input is starting from here to here, red one. The blue one is the seismic relative motion. There's a phase shift, phi. That is called as phase shift of this one. Now I can write what you call an amplitude ratio. Relative motion of the seismic mass divided by the vibrating object motion. The vibrating object is moving. That is called xing, correct? That can be equal to omega divided by omega n whole square, where omega is the input frequency, correct? This generally 2 pi f, we say that 2 pi fc, f is nothing but so many radians per second, omega. If the frequency, we say hertz per second, hertz, which is nothing but cycles per second. So f equal to omega divided by 2 pi, you can compute. Okay, so that is input frequency. Input frequency can vary, correct? If I vary input frequency, that will, but omega n is fixed. Please note that you can say this is based on system parameter, correct? Stiffness and mass, if that is known, the natural frequency of my accelerometer is fixed, it will not change. Similar damping ratio also, that's why they repeatedly telling for last 10 classes. The system output, time constant, natural frequency, damping ratio, all these things depends upon system parameters. Once the spring is selected with a particular stiffness, damper selected with some damping ratio, your seismic mass with some mass, then the accelerometer, omega natural frequency fixed, damping ratio is fixed. Here, this is input frequency. Omega is called as input frequency. That's what I told. It is going to, if you vary that, automatically the amplitude ratio mass. This is the equation. Take down the equation. Also, input acceleration, x in t equal to minus x in. This is displacement. Please know x in is a displacement. This is acceleration, input acceleration. Input acceleration equal to minus of x in omega square sine omega t. Correct? That means if from this you can find out that the acceleration, when input acceleration varies, automatically the relative acceleration of the seismic mass varies. If I am able to measure that displacement using a displacement sensor, the output is proportional to input acceleration. Okay, so this is a last, because it is slightly bigger derivation for you to understand. If any doubt, please ask me, then I can stop and explain. Hello. Okay. Then in this above equation, this equation, correct? We can be rearranged. We can write HA, okay? HAW equal to XR into omega n square divided by X in. This is relative displacement of seismic mass. This is input displacement of the moving object, vibrating object. Input vibration equal to omega n square divided by, can be 1 divided by 1 minus omega divided by omega n whole square. This is whole square plus 4 eta square multiplied by omega divided by omega whole square and root. Okay, so this whole thing is in root. That's what this half means, root. Okay, you can note down. Okay, now XR can be written as 1 divided by omega n into HA into X in omega. So this is what relative. The relative mass, not the seismic mass. In terms of system, this one you can say 1 divided by omega n square into HA omega into X into omega square, where the input acceleration amplitude is written by xi into omega n square equal to xr divided by omega n square divided by HA, where HA, when HA equal to HA omega, this part, the whole thing is called as 1. If it is 1, then we can say that the output x in, correct, xi omega n square equal to omega n xr, omega n square XR. Both are equal. Okay. If this term become 1, the whole term, when it become whole term, when you operate your accelerometer, whose natural frequency, for example, I have my natural frequency, x-axis 0 to omega, and this is my omega n. X-axis the frequency, right, in radians per second. Y-axis is x naught divided by x in, that is xr divided by x in. When I say, then it will be a flat for some this one, or after that it will start falling, correct? So if I operate below the omega n, so the accelerometer is connected, and if you are trying to measure acceleration less than omega n, then the input or the output of sensor is proportional to input acceleration. That's what we are trying to say. And HAW equal to 1, then we know that xi omega square equal to, this is input frequency, equal to natural frequency square made the relative displacement. So this we are plotting as a curve. So this is what I told you. My input frequency varying from 10 power minus 1 to 10 power 0 for a particular sensor. You can see that for different damping ratio. Already we saw spring mass damper system. The response output, this is nothing but omega. This is the amplitude ratio. Output divided by input. Right? Output is XR omega n square divided by X in omega is the amplitude ratio, will be a flat. That is up to, you can see that when damping ratio equal to 0.7, the curve should be flat for wide range. This is the X frequency. If they're going for longer, it is better. You can see that in this case, if my damping ratio is 0.7 and it is flat, this curve, right? I can measure this much range of frequency. So this is called a bandwidth. It's called bandwidth of the sensor. So from this, what we say is, you can design an accelerometer such that, right, the mass element, this mass, the damping ratio, and the spring stiffness is selected such that the eta is 0.7. So you can, when you design this one, if it's there, I will be able to measure frequency from 0 to the natural frequency, omega n, correct? My omega n higher. So this is my natural frequency, omega n. So I can operate, I can measure up to, this is my natural omega n. I can operate up to this. You can see that this is flat. If I select 0.7, for others, it is coming down much before. Otherwise, there are peaking. They call overshoot. Overshoot is not allowed. So I want flat curve. So the accelerometer design such that is eta is around 0.707, so that I can measure up to close to 0.707 times the omega n. Up to that frequency I can measure. My input frequency can be omega 0 to this much I can vary. So that is range for which the accelerometer can be used. Okay. Now I just complete this today. Then we can talk about other things later. So now for the second order system, the accelerometer, if I give a step input, the input is given in green color. You can see that suddenly at t equals 0, I gave a step input to it. Then depending upon damping ratio, already we know eta is called a damping ratio. If damping ratio greater than 1, correct? What will be the output? You can see here. When greater than 1, it is called over damped system. The blue color lines, correct? So it is very slow. The lot of time delay. This is called settling time. Settling time will be larger. And it takes some time to output to reach the input value. Instead of that, if eta is less than equal to 1, it is called critically damped. That is shown as a black color line. You can see here. This is output for C-spike is a sensor, accelerometer. If eta equal to 1, the output will rise like this, black color line. Correct? You can see that the settling time TS is this. TS is this much. Okay. For eta equal to 1, critical damp. If it is a, and when eta is greater than 1, it is called as over damped system. Correct? You can see the settling time is larger. So which is better? I told you, lesser the settling time, better the sensor. In fact, I want the settling time should be 0. That will be there possible only for 0th order system. But you cannot make an accelerometer using just only a energy dissipating element. using a damper. You need spring and mass all together, then only can construct, then automatically become a second order system. So the response, then the eta comes what you call damping ratio. Damping ratio, already we know the equation, correct? So damping constant divided by critical damping. So in that case, it can evaluate anything. So the third one is the under damped system. If the eta is less than 1, anything 0 to less than 1, correct? 0.9999, whatever you can say, less than 1. This range is called as under damped system. In that case, you can say red color. If I give us a green color, same input, green is the input for different this one, you can see that it goes, this is called as overshoot. Already we talked about it, right? Overshoot, and it moves up, and then after some time it settles down. So the settling time is, you can see that mode. This settling, it become constant after this. So depending upon damping ratio, the different values are coming, right? Now the whole thing is, for how will you find out the output? Output y of t equal to, this is equation. If the over damped system, if the damping ratio greater than 1, it is called as, greater than, we call over damped system. For this, output y of t can be calculated using this equation. Please see that what is there in the equation. Everything in terms of eta only, eta omega n, right? Nothing more than that. Already you know omega n equal to, we know that root of k by m, correct? And eta equal to c divided by root of 4 mk. Once from the system, when you calculate, you substitute the value, and the E is called natural log. You take natural log, and then you can get this curve was got using this equation. Please note that this curve was got using this equation only. Over damped system. If it is under damped system, or okay, when eta equals 0, it is called as undamped system. The output equation will be like this. What will be, if I give a step input, the output will be like this. For same this one, it will oscillate. You can see here, x of y of t equal to input multiplied 1 minus cos omega nt. Cos means sine, it is a vary with phase shift of 90 degree. Correct? So I gave a step input, output is oscillating. So that is called an undamped system. That is no use. I gave a step input, output should go like this. Instead of that, it is oscillating like this. Undamped system will oscillate. That means damping ratio equal to 0. And if damping ratio less than 1, it is called underdamped system. This is equation. Let me clear this. You can write, right? For underdamped system, y of t output equal to this equation. This curve was plotted using this equation. Okay. Then, if it is a critically damped system, this one was computed using this equation. These are the 4 different type of equation using which you can calculate the as the time varies. In this equation, how will you find out, plot this curve? Anybody can tell? Just 2 minutes I will close it. Today I want to close this. Okay. How will you find the system response? For example, I given K, Ks, M and C values are given. That's it, nothing more than that. Then what do you have to do? Somebody can respond.
Substitute, sir. We have to substitute it in the, to find out the CC, omega n, everything.
First you calculated the omega n.
Omega n equal to?
Omega n equal to already root of K by M.
K by M. Yeah.
Then you find out delta equal to C divided by root of 4 mk. You
yes,
calculate.
already all. Yes,
then omega d equal to omega n multiplied by root of 1 minus eta. Note down.
Right, sir. Right, sir.
The omega d is called damped natural frequency. The d represents damped natural frequency. Okay, this you are done. Once you are done, then substitute this value. Wherever omega n is there, you substitute that. Wherever eta is there, substitute that. That is first thing. Next thing is what you will vary. The t is varying. Everywhere t is nothing but time with respect to time. Right? You t equal to 0. You substitute all value. Everywhere you substitute t equal to 0. Okay? Then you will get y of t, you will get one value. some XX value. Then I say T equal to 1. Here, everywhere I say T is there, I will substitute 1. Okay. Then I compute this is Y of 0. I say Y1 of T. I get some YY value. Then I make T equal to 2 in this equation, wherever T is there. Because once you computed eta, omega n, omega d, all these things are fixed. Only thing varying a T. If I vary, that means you will get points. Then connect, you get the curve. That's how you draw. So in the exam, suppose if you say the underdamped system, points underdamped system means you have to use this equation. Underdamped system, how do you find out? First, you have to find the eta. Compute for given value of damping constant, the mass and stiffness. You find out what damping ratio. If damping ratio is less than 1, you can use this equation. In this equation, you substitute the values. X of t is given, right? I given a step input, right? So 0 to 1, this will be 1. What I do? I will vary the t. 1, 2, 3, 4, wherever t is coming, you will vary that. Compute this value and plot it, draw it. Then connect that, you will get the output response, how it will be. Whether it will be like this or will be like this, you can find out. I stop here. Okay. So we have seen different type of sensors and definition of sensors. 0th order, first order sensor. I saw three. For each I am given one example. 0th order sensor, potentiometer, first order sensor, thermometer, the second order sensor, the accelerometer. So we many types of force sensor, torque sensor, all those things can be come in one of this. If you write the equation, if it is algebraic equation, then it is called a 0th order system. If the equation become a first order differential equation, you say first order system. The equation will be a second order, like that will be. Any doubts?
Sir,
Yeah.
sir, sir, this equation and all we have to memorize and we have to write, sir.
You don't want that?
No, sir.
I thought
Sir,
simple equation.
Even reading itself, it is taking time, sir. How people are memorize it?
Just a request that, like, if it is possible, like, if we can, if you can provide a formula sheet, like, with a list of formulas along with the question paper, that can be helpful for the team.
Okay, so I am not going to do that. Then everything formula, the simple. I will not ask this kind of questions. Plot y of t, correct? This I won't ask in the exam. Okay, this is a guarantee.
Okay.
Other simple formulas. Okay.
Thank you.
I take consider you also. I know that you are industry last 10 years of working. You are not.
Sir, we can memorize it. Even one or two parameters we shift like this side, that side. Now that will create a what you call, sir. Totally, we will collapse there.
I understand. I am teacher for VMaster for last 7 years.
Right.
I am always considerate. I know it is, you are not wantonly doing. Avoid. See, your intention is not to avoid wantonly, correct? And
Yes,
I know the limits because you are interested in learning. Certain things are difficult for you because of the factors. Age, you do not expose long gap between studies, all those things. I understand. This I won't ask you to plot this curve. Okay.
Sure.
But you'll be asked to
Thank
find out the time constant, natural frequency, damping ratio, all these things. They are very, very simple. Right? Omega n, omega d. That's a very simple. For that and all, you cannot take formula sheet. Right? Very
Sure,
simple.
sir, sure,
Okay. This I won't have. I respect. No, I know. See, I'm also becoming old. No. As a professor, I'm also getting old. I know what difficulty you are facing. It is not that I don't understand. I won't ask this question even in insult. They only for your understanding. Okay.
Thank you, sir. Thank you.
Thank
That
you.
is guaranteed.
Thank you.
Okay.
Thank you.
See
Have a nice
yeah. See you on Monday. Enjoy your weekend carefully.
Thank you, sir.
Okay.
Thank you, sir.
Sure, sir. Thank you. Thank you.
Thank you.
Sure, sir. Thank you.
Thank you, sir.
Okay. Give your attendance
Thank you,
before leaving.
sir.
That is more important. Attendance will be.
Thank you, sir.
Yeah. Thank you. Take care.